it a hard? Well, it should be a medium. What can I say? This is 1671 minimum number of removals to make mountain array. If you watch all my videos, you know that I like to rhyme the title of each problem, just as a little joke. But I've had to rhyme the word array so many times that I wish the word array would just go away. But that doesn't matter. So this is a hard, but it's definitely a hard. But it could also be classified as a medium, and I wouldn't blame anybody. So that's just something to be said. So let's go ahead and get right into it. So you may recall that an array is a mountain array if and only if the array length is greater than or equal to 3, and there exists some index I where everything less than index I, it's increasing to I, and everything after I is decreasing, like a mountain, right? So it increases, it hits a point, and then it decreases. Pretty straightforward, right? How mountains work, and that's how mountain arrays work. And of course, the increasing, decreasing is about the value at that index, right? So from 0, it increases all the way up to I, and then after I, it decreases all the way up to the end of the array. So we're given an integer array nums, return the minimum number of elements to remove to make nums a mountain array. So you might be looking at this saying like, whoa, that sounds pretty hard, right? And this is definitely one of those problems where it is hard, but if you start playing around with it a little bit and start thinking about things in terms of other things, right? What's an equivalent way of looking at something? You'll realize, well, if you studied data structures and algorithms before, you've probably solved an identical problem, right? A kind of a sub-problem of this problem, right? You've already solved this most likely. And that problem is, I'll tell you in a second. But the thing is that this problem is really just a little bit more complicated version of a problem you probably already solved because it's so popular. And then once you realize this, you say, okay, maybe this isn't a hard, maybe this should just be a medium. But, to each their own. It's really, I guess, the hard part of this problem is the intuition to realize that, oh, this problem is really just a restatement of something that I've already solved. Okay. So when we look at 131, let's go ahead and, this one is obvious, right? Because it's already a mountain array. Why is that? Well, it goes from 1 to 3 to 1. Okay, let's look at this one because it kind of, it's a little more involved. So hopefully it'll provide us with something that we can use to kind of gain some intuition about the solution to this problem. Now the constraints, well, we have nums is greater than or equal to 3. So it's guaranteed that you can make a mountain array. Okay, so there's always some way to make a mountain array in the system. Okay, it's not like we're going to be given a problem where it's impossible to make a mountain because it's all increasing or all decreasing or something like that. And 1,000. So what does this 1,000 indicate? Well, if you've watched my videos before, any other YouTubers, right? There's something that the constraints indicate, and that's that. Okay, n squared. If it's 1,000, n squared would be 10 cubed. 1,000 times 10 cubed. 1,000 times 1,000, 10 to the 6th, and that's cutting it close. But any solution that's roughly x times 10 to the 6th in its worst case runtime complexity will pass and not result in time limit exceeded. So what this tells me is that if we find an n squared solution, we'll be good to go. Okay. Now let's go ahead and write this example out. So for example, we have the situation 2, 1, 1, 5, 6, 2, 3, 1. Now to really just bring the point home about how this works, let's actually make mountains out of this, okay? So this is the first hill, I guess, or I don't know how you want to articulate this, but it has size 2. There's one here with size 1. There's one here with size 1. There's one here with size 5. 2, 3, 4, 5. There's one here with size 6. All right. There's one here with size 2. There's one here with size 3. Let's redraw that one. I don't know why I keep messing up this one. Size 3. Looks better. And then there's finally one here with size 1. Okay. So, how are we going to make a mountain out of this, right? We need something where it's like an obvious mountain shape, right? It's increasing to a point and then decreasing, or increasing from one side, increasing from the other side up until that point. One solution is to remove the elements at index 0, 1, and 5. Okay, so if we take this thing, okay, and we remove the elements at index 0, 1, and 5. Okay, well, let's write down the indexes, right? So the indexes are here. So he's saying 0. So we remove this thing. 1 and 5. All right, so if we look at this, we say, okay, so we're going to remove 0, 1, and 5. And then this resulting, I guess, array looks like this. And you can tell that obviously, right, this is a hill, right? Because it goes up to this point and then back down. Okay. So there we go. And this is the shortest solution, okay? So how are we going to look at this problem and figure out what we need to do, right? Because we need something that's, like I said, something in the O of n squared time in the worst case. And we need to find the minimum things to remove, right? Because like when you look at this, it's like, okay, you know, we got to remove 2. Like if I want this to be the top, well, it can't decrease then increase again. So I need to get rid of this, right? Okay, I'll get rid of one of these because it has to be increasing. So it can't just be 1 and 1. And then like this thing's pretty obvious, right? Because it goes up and then down. And then we want to remove this, right? So one way to first look at this problem is say, well, we want to create 2 increasing arrays. 2 increasing arrays, right? From left to right and 1 from right to left. Okay, now this will make sense why I'm making this distinction here. And sometimes that's what happens in these problems, right? You have to make kind of obvious identical statements because those obvious identical statements will indicate something about how you can solve this problem, right? You know, saying something that's increasing and then decreasing, right? You don't even really need to say it like this now that I'm thinking about it, but, you know, it's easier to think about in these terms, right? We want to find, you know, an array that's increasing from the left to the right, right? From left to right, we want it increasing, right? And then from right to left, increasing as well, right? And then wherever these things meet, right, that would be the 2 increasing arrays that we're going to be making, right? Now, in order to make an array increasing, well, what do we have to do? Well, we have to remove things that make it non-increasing up to a point. And what I mean by that is like, if I want to make this system increasing, right? If I have 2 and then 1, well, I can't make it increasing to 1 to 1 to 5. If I want to make it increasing from here to here, well, I'm going to have to remove some elements, right? I could remove, you know, these 2 elements, so then it's 2, 5, or I could remove, you know, of multiple solutions. In this case, I can remove these 2 elements and it's 1, 5, right? But I'm trying to find increasing arrays going in both directions, right? So if I find increasing arrays going in this direction, increasing arrays going in this direction, the intersection point saying, okay, a hill is really, what's the longest increasing array I can get from the left? What's the longest increasing array I can get from the right? And meeting at some point, okay? So let's think about that here. And let's use that way of thinking this, like, okay, I'm trying to get 2 increasing arrays, right? An array that increases from left to right and an array that increases from right to left. And the point that they meet, right, that's the top of the hill because everything from my left is increasing from left to right and everything from my right is increasing from right to left. And that meeting point is the top of the hill, okay? So how is that the same problem? Well, you know, we're trying to find the minimum number of elements to remove, right? And one way you could think of that, another point here is minimum to remove is logically equivalent. I'm going to use 3, you know, something I learned at school. Minimum to remove is equivalent to maximum to keep. Right, so here's kind of 2 things to think about when you're solving this problem, and you can see that it's really the equivalent thing, right? A mountain is, you know, it's increasing from left to right, hits a point, and then decreasing from left to right, starting at that point. Or it's the same thing as saying increasing from left to right and increasing from right to left, and then the point that they meet at, right? And also, the minimum to remove, when we're trying to find the minimum things to remove, that's the same thing as stating the maximum to keep. Right? Those are equivalent statements, right? We're trying to remove the least amount of people. That's the same thing as saying we want to keep the maximum number of people, right? Those statements are logically equivalent, right? We want to remove at one most people. Okay, well, then we have to keep at least, if we have 10 people, we want to remove at most 1, then we have to keep at least 9, right? So these are equivalent statements, right? Minimum to remove is maximum to keep. So how do we find, the equivalent statement is, well, how find left to right maximum elements increasing? How find right to left maximum elements keeping? So that's what we're doing, right? This problem is equivalent to saying left to right, right to left, and instead of minimum to remove, we're trying to do the maximum to keep. Okay? So how do we find left to right maximum elements increasing? This is literally just the longest increasing subsequence. Right? The longest increasing subsequence is the longest increasing subsequence. Longest increasing subsequence is a problem you've already seen before. Right? That's the problem where you're trying to find the minimum number of elements to remove to create a subsequence such that each element is increasing in order, right? And we'll go through the n squared solution. There's actually an n log n way, but n squared will meet here, and we can just mention that there's an n log n way. But really, if you know how to solve longest increasing subsequence, which is the maximum subsequence within an array, then you know how to solve this problem. You're just going to do it twice. You do it for left to right, you do it from right to left, and at each point, that's the longest increasing subsequence ending at that point. So you look at the one from the left, the one on the right, you see how long those subsequences you can create are, and that would be the maximum number of elements you can keep. So then the length of the array minus that would be the number of elements you have to remove. Okay, so we'll go through this really quickly, and then we'll think about the implications of this in the problem. Ugh. Some things are going to get lost along the way. It doesn't really matter. Okay, so let's do the longest. We'll do it left and right. Okay, so longest from the left and longest from the right. So since we're starting from the left, how does this work? The longest increasing subsequence starting at 2 is just 2 itself. At 1, well, in order for it to be the longest increasing subsequence, I'm going to go through this quickly because if you're doing a hard problem, right, the idea should be that you already know this algorithm. This algorithm should be deep within your brain because it's such a common interview question. And if you're doing a hard, you should probably already know how to do this. But I'm going to go through it really quickly, okay? Longest increasing subsequence ending at 1, starting from the left, is just 1 itself because 1 can't attach itself to 2 because that's not increasing. So it's just 1. This one is 1 plus, well, it can't attach itself to this, and it can't attach itself to this, so it's still 1. Okay, what about 5? Well, 5 can attach here, here, or here, right? So the longest it can get is 2, because it can attach to 1 of length 1, 1 of length 1, or 1 of length 1. So that's itself plus 1 is 2. Okay, how about 6? 6 can attach itself to this 5. It can attach itself to this 1. It can attach itself to this 1. Attach itself to this 2. Obviously, if you want to make the longest one, well, then 6 should attach itself to 5 because 5 has length 2. So 6 will become length 3. This 2 can attach itself to 6, to 5. It can attach itself to 1, 1, 1, 2. This 3 can attach itself to 2. It can attach itself to 1, or to 2. This one has length 2, so it'll be length 3. This one can't attach itself to anything, so that's length 1. So the reoccurrence relationship here, right, is L of I equals 1 plus L of J if nums at I is greater than nums of J. So this is the very simple recurrence relationship for, finding the maximum subsequence in n squared time, right? Because for each element, you have to look at all the elements before it to see if you can attach yourself to it. But it's pretty intuitive, right? The highest subsequence I can make here increasing is, well, I can attach myself to anybody who's less than me, so I'll just attach myself to the person that's less than me that has the greatest number of longest increased subsequence for them. Okay.
All right, and then the right thing, we do the same game. I'm going to play the same game here. So 1 to 3, 3 can increase 1. This is 2 to 2. This can do 2 because 2 can attach itself to 1. 6 can attach itself to 3. 5 can attach itself to 3. 1 can't attach itself to anything. 1 can't attach itself to anything. 2 can attach itself to 1. Okay? So what these points really represent, right? These points represent the maximum subsequence to the left and the maximum subsequence to the right. So the maximum one, right, would be this 6, right? Because this 6 can attach itself to 2 things to the left and 2 things to the right, right? So this 6 really indicates, okay, I have 2 to my left and 2 to my right. Okay? So how many did I have to delete to create this? Well, how many elements are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 elements. That's the length of nums, right? Well, I don't have to delete myself because I'm the top of the mountain. So I'm -1 for myself, right? I'm going to do this a different color because it's hard to see. Right, so what's the reoccurrence relation? So there's length of nums elements originally. Now my longest subsequence on both sides, that tells me how many elements I used, right? So that's the amount of elements that I kept. So the number that I removed is the length of nums minus that. Right, so I keep, there's length of nums in total, and how many did I end up keeping? Right, I ended up keeping a subsequence to my left minus L of I, and that's this L of I for the max one. So I'm going to color code this so everything. So this is L of I, and then my subsequence to the right, which would be R of I. And then I overcounted once, right? Because I'm counting this 3 twice, right? Because there's 2 to my right that I'm including, and there's 2 to my left that I'm including, and then myself of 1 make 3. So then just subtract 1 from that. Okay? So really what this relates to, right, is, well, what's actually making this mountain happen? Well, what's happening is I'm using this 6, right? And then I'm using 2 to its left. So I'm using this thing, and I'm using, I don't know, let's just say I'm using this. Okay, because I can use any of those 3 to make this happen. And then from the right, well, I'm using this 3, example, and this 1. Right, so if I'm making the subsequence, I'm using 1, 2, 3, 4, 5 things, right? I'm using 5 things, so 3 and 3 minus 1, because I'm counting the same things twice. So that's 6 minus 1, 5 things. So this is all the elements I'm using. Then how many did I have to delete? Where I had to delete the only ones remaining, right? So I had to end up deleting these red ones, right? So that's the number that I had to delete to make this work, right? So this is the number that I kept, the longest increasing subsequence from the left and the longest increasing subsequence from the right. And the ones I removed are just the ones that are left over, right? So the ones that I removed are the things that I'm not using. So that's just length of nums minus the things that I'm using. Okay. So let's go ahead and write the code for this and call it a day. And then there's one thing that we have to consider, just a little stipulation about how this is supposed to work. Okay, so every mountain starts itself is length 1, right? That's the longest increasing subsequence. Longest increasing subsequence to the right is also length 1. And then we'll just go through the entire array. So we'll go twice length of nums, and then twice. We'll go through length of nums from the left and length of nums from the right. So if we're going from the right, you gotta do that terrible thing in Python. We'll say, okay, L of I is, well, it's 1 plus the max that we can get, right? So the recurrence relationship, we already looked at it, right, is 1 plus L of j if nums of I is greater than nums of j. So you just say 1 plus L of j for j, everyone that's to my left, if nums of I is greater than nums of j. Now, it's possible that there is no such candidate, so we'll do a default value of 0. right? If there's no one to my left that I can attach to, I can attach to 0 people, so then it stays length 1 here. So I guess that could be 0. I don't want to mess with it too much. Okay. All right, and then this is the same game here, except now we're going to update right, and we're going a different direction, right? Because now we go from the length of nums -1 all the way to I. So we're going negative direction. And it's the same thing, right? So I'm basically saying the longest subsequence I can get here is 1, including myself, plus the longest subsequence I can attach to. If I'm going to be an increasing subsequence, I have to be greater than the thing that I'm attaching myself to. Okay. And then at the end, we just return the max. Well, what was the formula? We said the length of nums, that's the total number of elements. I had to remove whoever I didn't keep. So I kept the subsequence to the left. I kept the subsequence to the right. And then I -1 because I'm overcounting, or +1 because I'm overcounting by 1, right? I'm counting the peak twice because I'm saying the longest subsequence including this, the longest subsequence to the right including this, okay? And then we're going to do, we can try everything. So for I in range length of nums. Now, there's one catch, and this is going to fail here. So don't think I don't have a control of what's going on, but this is not going to work. Well, it's going to work maybe for the example, but there are cases where this doesn't work. And that is because what? So this says 2. It should be -1. What did I do wrong here? That's why it's always good to just have your code written down. -ri -1 here. I think. All right, so always a good thing to do when you're troubleshooting, right, is to print out your L and your R. Right, print out the things that you're populating to see if they make sense, right? It should be 1, 2, 1 for both directions because it's just 1, 3, 1. Okay, so this should be 2 here, right? Because the longest thing is oh, because I put J here for some reason. I don't know why I did that. I'm pretty sure this should be +1. Because I'm over counting twice, so I have to add 1 back in. Okay, this is 2 and 2 and 1. So if I choose this, I should get 4. Length of nums is 3. Minus -2. Oh, so this should be minimum. Oh my gosh. Sorry, guys. I want the minimum difference, not the max difference. Okay. Growing pains. I don't want the minimum. I want the minimum number of elements to delete. All right, so this is saying it's 1 when the answer is really 2. Why is that the case? Well, the thing is, what this is going to want to do here, right, in this problem is it's like underselling, right? It's overperforming, I guess. It's saying that it can make it that there's only 1 thing we have to delete, but really the answer is 2. And why is that? Like if this works and I can delete more than what it's saying, then I have a better solution, right? But I only have to delete 1 element, but it's saying I actually have to delete 2. Well, the problem is it's choosing this answer here, right? And you can't choose anything where the longest increasing subsequence is just 1. All right, so we're going to say if L of I is greater than 1 and R of I is greater than 1. Now this is going to work. Now, why is that the case? Why can't the longest increasing subsequence just be 1 in either direction? The longest increasing subsequence can't be 1 in either direction because that means that the element itself is the longest increasing subsequence, right? Like you'll notice here, what's the longest increasing subsequence? Just 1. Nick, there's 1s here, right? So what does that mean? That means that there's nothing to the left that this can attach to, right? Because these points that we're choosing, L of I and R of I, those are the peaks. So this is the peak and it has value 1. That means there's nothing to its left that it can attach to, right? Because if it was value 2, that means there'd be something to its left that I could attach to. But if it's just value 1, that means there was nothing to its left to attach to. So then it's not a mountain, right? A mountain has to have a value on its left and a value on its right. At least one value on its left and at least one value on its right. This value is 1, so it has nothing on its left to attach to. So then it can't be a mountain solution. So there always is a solution, right? That's what this is saying, right? That's why we didn't need a default value here, because there is always a solution. It just may not be what you get when you have the longest increasing subsequences in both directions, right? There's still the case where if it's just 1, there's nothing you can attach to, so that can't be the actual solution. Okay, so again, this process here can be done in n log n time. So this solution could be n log n, but for now, let's just say that n equals the length of nums. Now for time, we go through each array, right? And then for every element, we have to look at all the previous elements. So that's n squared. And the at sign, I wonder what that means. And then for space, well, we create this L array, this R array, and then we just populate it, right? We don't do anything else. So we create, it's n space, right? Because it's the size of nums, and we do that twice, so 2n, that's just big O of n. Now, technically, with LIS optimized approach, this is big O of n log n. So there is a faster way of doing this, but I'm not going to spend time doing that, because really this problem isn't about, right, longest increasing subsequences. This problem is knowing, okay, how do I take this mountain array ID and say, okay, I need the longest increasing thing from the left, the longest increasing thing from the right. Oh, that's just longest increasing subsequences twice, and then I just take the maximum of that, right? It's really the application of a simpler problem. That's, I guess, what makes this hard. So how do I take a complex problem, think about it in terms of simpler problems that I've definitely solved before because it's so common, and then apply that to find the optimal solution, or, you know, suboptimal but within the boundaries of what's accepted. All right, peace out.